All right, welcome to Thermodynamics ePortfolio Project 1. My name is Nate Lohmeyer. This first video we'll be doing a chapter summary of chapters 1, 2, and 3. So we'll begin with chapter 1. So the big things that we talked about in chapter 1 were the idea of systems, conservation of energy, and how it's related to the first law of thermo. We also talked about properties, quite a bit, what those are. The zeroth law of thermodynamics, pressure, various other things. I'm going to kind of start with systems here first. So we kind of divided things up into a couple different types: closed systems and open systems. In a closed system, there is no mass transfer, but energy can transfer back and forth. So in a closed system, there's a fixed amount of mass, so the mass can't cross a boundary. This is an important concept as we'll have closed systems where the mass can't move, however heat or energy can be moved in and out of there. It'll be important for our considerations later on in chapter 2. So moving on to conservation of energy and first law of thermodynamics. The conservation of energy principle more or less states energy cannot be created or destroyed. It can only change forms. So we'll be talking about that quite a bit. The first law of thermodynamics asserts that energy is a thermodynamic property. In regards to properties, we talked about extensive, intensive, and specific. So with extensive properties, they're dependent on the size of the system and or the mass of the system, whereas intensive properties are independent of the mass of the system. So some independent properties include temperature, pressure, and density, whereas dependent include volume and energy. And then specific properties are an extensive property per unit mass, so it's usually like the specific volume would be the volume divided by the mass to get the specific volume. We also talked quite a bit about just the importance of units and conversions and making sure that we have dimensional homogeneity within our equations and as we're solving. So that kind of wraps up the major points of chapter 1. Now we'll move on to chapter 2. So chapter 2 was a little bit more involved than chapter 1. Chapter 2, we talked about forms of energy, work that's done, first law of thermodynamics, and how the energy of the system relates to the change in the total energy of the system. We also talked about the three mechanisms of heat transfer: conduction, convection, and radiation. And we also talked about fluids flowing across control surfaces and control volume and how they transfer energy into heat or work. So starting with energy, we talked about the kinetic energy, Ke, which is equal to 1/2 m, or the mass, times velocity squared. velocity is important in kinetic energy because obviously it's something moving. So kinetic moving, is always going to be a velocity term. The next is going to be the potential energy, which is equal to the mass times gravitational constant times z, or your height. And then finally, the concept of internal energy, or U, was introduced. U, or the internal energy, is the sum of all of the microscopic forms of energy within the system. Together, they equal the total energy of the system. So E equals U plus KE plus PE, which is equal to U plus 1/2 mv squared plus mgz, which is an important formula for us. Alright, we also introduced the idea of E dot mech, or the rate of mechanical energy of a flowing fluid, which is equal to m dot, which is the mass flow rate, times E mech, which is equal to m dot times pressure over density plus v squared, or velocity squared, over 2 plus gz. We also talked about conduction, convection, and radiation. Remember that conduction is transfer of energy between particles, like within solids. Convection is between fluids, and radiation is the transmission of energy due to electromagnetic waves. Next, we moved on to work, which in the mechanical form is more or less a force acting over a distance, and that's measured in kilojoules. And finally, we introduced the concept of energy balance, or the energy that's going into a system minus the energy going out of a system is equal to the total change of the energy of the system, which, as we'll see in a later problem, is equivalent to dE dt, or the rate of change of energy, of internal, or rate of change of energy in the system. So finally, we'll move to chapter 3 here. So chapter 3, we talked a lot about the properties of pure substances, which we defined as a substance that has a fixed chemical composition throughout. And then we talked about the phase change processes. We learned about PV diagrams, TV and PT diagrams, which PV and TV we used quite a bit as we looked and learned how to solve problems using the different tables in the back of the book, which are all derived experimentally to help us solve problems. In chapter 3, we also talked about ideal gases and the ideal gas equation of state, and how it can be used. So I guess the first thing we'll talk about here are going to be just the phases. We talked about compressed liquids, saturated liquids, saturated vapors, saturated liquid vapor mixtures, and superheated vapors. How we can determine which is which based on the values for specific weights in the tables. If the value of VF, or of V falls between VF and VG, we know that it is a saturated mixture. If the value of V is equal to Vg and the temperature is above what the chart says, or the pressure is above what the chart says, we know that it's a superheated vapor. We can also calculate what's called the quality, X, which is equal to the mass of the vapor over the mass total. If that's equal to 1, then we have a saturated vapor. Another really important equation that we learned was, we'll call it Y equals YF plus X, the quality, times YG minus F, which in this case we can substitute for Y, can be either U, the internal energy, V, the specific weight, H, the enthalpy, or S. We can use the tables to help calculate any one of those variables given the information that we have. It proves to be a very powerful equation for helping us solve problems. And finally, we talked about the ideal gas equation of state, which is the pressure times the specific volume equals the gas constant R times T, which, if we are comparing multiple states, we can rewrite it as P1 V1 over T1 equals P2 V2 over T2. And given a couple of the variables, we can solve for our missing one, which is important. Keep in mind this is for ideal gases only. Well, this kind of concludes our summary of chapters 1, 2, and 3. Hope we've answered all your questions. Thank you for your time.